Muthuraj, an assistant professor in Tirunelveli Engineering College, PSN College of Engineering and Technology. Here we are going to see about the subject and its material related to about a key capsule of fluid mechanics and hydraulic machinery. Let's we start with the basic things of something else like properties of fluid. For the properties of fluid, here we have to classify the contents as of four columns: properties, formula, unit, and dimensions. And the properties were density, and the formula for density was rho is equal to m by v, which is mass by volume, and the unit of density is notation. The notation was given as kilogram per meter cube, and the dimension was m, which means capital M. The mass, the kilogram, which can be denoted as mass, capital M, and meter can be denoted as length, and ml power of -3. And the specific weight, the formula for specific weight, W is equal to capital W by capital V is equal to small m g divided by V is equal to overall. The specific weight can be given as rho of g, which means that the rho can be finalized as previously mentioned density, and the specific weight small w is equal to rho g, and rho of water and W of water is equal to 9.81 into 1000. The 1000 is density of water, as we all knew about it, and the unit of specific weight is Newton per meter cube or kilogram per meter square by into second square, and the dimension was capital M, capital L power -2 and capital T power -2. And for the specific gravity, S liquid is equal to density or weight density of liquid divided by density or weight density of water, and the weight density of liquid is equal to specific gravity S into 1000 into 9.81 Newton per meter cube, and the density of liquid is equal to S into 1000 kilogram per meter cube, which is unitless and it's dimensionless. The specific volume, small v is equal to capital V divided by M, which is abruptly the reciprocal of density, which is equal to 1 by rho, and the unit also reciprocal, meter cube per kilogram, as well as the dimension becomes M, capital M of power of -1 and L, capital L of power 3. And for bulk modulus, K is equal to minus of dP by dV, d capital V divided by capital V is overall, which is the derivative part of rho and volume. The unit of bulk modulus is Newton per meter square, and the dimension was capital M, capital L power -1 and capital T power -2. And compressibility, for the compressibility, which is reciprocal of bulk modulus, beta is equal to 1 by K, and the unit of compressibility is meter square per Newton. And for the dimension was capital M power -1 and capital L, capital T of power 2. And for surface tension, the formula was sigma is equal to F by L, and the SI unit of surface tension was Newton per meter, and unit of surface tension, CGS unit of surface tension is dyne per centimeter, and the dimension was mass M, capital T power -2. And for the vapor pressure, force by area, PV is equal to rho V is equal to force by area, and the SI unit of vapor pressure was Newton per meter square, and the CGS unit of vapor pressure was dyne per centimeter square, and the dimension was capital M, capital L power -1 and capital T power -2. And now we are going to see about Newton's law of viscosity. The Newton's law of viscosity can be given as tau is equal to mu into du divided by dy is also known as, can be given by mu into d theta by dt. And as I mentioned, mu into du by dy, the du by dy can be given as velocity gradient, and d theta by dt can be given as rate of shear strain or shear deformation. And dynamic viscosity, here some important things about the dynamic viscosity are delivered as on my aspect. Dynamic viscosity, mu is equal to tau divided by du by dy and some specific notes are viscosity of fluid is measured by viscometer instrument and it is measured only on flow condition, and viscosity of liquid in varying condition is measured by rheometer. Seibold, redwood and Engler devices used to measure kinematic viscosity of fluid. Mu water is equal to 55 mu air, 55 times of mu air at 20 degrees Celsius. At 20 degrees Celsius, dynamic viscosity of air, which is 55 times of dynamic viscosity of water. And for liquid, if temperature rises, pressure rises, dynamic viscosity will get reduced or it will be maintained as constant. If temperature rises, dynamic viscosity will reduce. If the pressure increases, dynamic viscosity will there will be no change in dynamic viscosity. For gases, if temperature rises, dynamic viscosity will increases. If the pressure rises, there will be no change in the dynamic viscosity, which means we can conclude as the dynamic viscosity will never face any change when the pressure gets increased or decreases. Unit of viscosity for the SI unit was Newton second per meter square or Pascal second, and for CGS unit dyne second per centimeter square, and MKS unit are kilogram F second per meter square, and for 1 poise is equal to 1 by 10 Newton second per meter square, and 1 centipoise is equal to 10 power minus 2 poise. And now we see about kinematic viscosity. The kinematic viscosity is Veta is equal to dynamic viscosity divided by mass density, which means previously seen dynamic viscosity, which is mu divided by rho, and rho of air is equal to 15.2 times of rho of water at 20 degrees Celsius. For liquid, if temperature rises, kinematic viscosity decreases. If pressure increases, kinematic viscosity will maintain as the previous values are as like constant. For gases, if the temperature increases, the kinematic viscosity will get increases. If the pressure increases, the kinematic viscosity of gas will get reduced. The SI unit of kinematic viscosity is meter square per second, and CGS unit of kinematic viscosity is centimeter square per second or Stoke. 1 Stoke is equal to 10 power minus 4 meter square per second or 1 centimeter square per second, and 1 meter square per second is equal to 10 power 4 Stokes. Kinematic viscosity of air always greater than kinematic viscosity of water. Surface tension is due to cohesion only. Surface tension sigma is equal to force by length, and sigma is also can be given as another formula as work done divided by increase in area. For liquid, surface tension, if surface tension decreases with increase in temperature. For gas, surface tension increases with increase in temperature. Relationship between surface tension and pressure can be given with the conditions and its pressure. Pressure inside droplet, if the material is if the object is a solid as sphere, the pressure P is equal to 4 sigma divided by D or 2 sigma divided by radius R. And pressure inside bubble or hollow bubble like soap bubble, the pressure P is equal to 8 sigma by D or 4 sigma by R. And pressure inside liquid jet's units are D is equal to dia of bubble and sigma is equal to surface tension, and the pressure of that pressure inside liquid jet P is equal to 2 sigma by D or sigma by R. The surface tension is measured by tensiometer or stalagmometer or stactometer or stalagmometer. Capillary action is due to both cohesion and adhesion. Capillary tube, the capillarity of the capillary tube H is equal to 4 sigma cos theta divided by rho GD, which also can be simplified as 4 sigma cos theta divided by WD. And capillarity in parallel plate H is equal to 2 sigma cos theta divided by rho GT. And capillary rise or fall of liquid in, if capillary rise, the theta of capillary rise is less than 90 degree, adhesive force greater than cohesive force and wetting surface. If the capillary fall greater, theta of capillary fall greater than 90 degree, cohesive force greater than adhesive force and it is also non-wetting surface. The contact angle theta is, if the theta is 0 degree Celsius, 0 degree for pure water and glass tube. If the theta is 8 degree, the objects are water and glass tube. If the theta is 128 degree, the objects are mercury and glass tube. If the theta is 26 degree, the objects are kerosene and glass tube. The capillary action occurs due to combined effect of adhesion, cohesion and surface tension. And the types of fluids are ideal fluid, it is incompressible and have no viscosity, and real fluid, it possesses viscosity and compressibility. Ideal plastic fluid, in this shear stress, the shear stress is more than yield value, and the shear stress can be notified as tau proportional to du by dy or d theta by dt. The Newtonian fluid, in this type of fluid, the shear stress is directly proportional to rate of shear strain, or Newtonian fluid does not change with viscosity or with the rate of deformation or shear strain. The example of the Newtonian fluids are water, kerosene, petrol, benzene and ethanol. And non-Newtonian fluid, in this shear stress is not proportional to the rate of shear strain. This fluid does not obey Newton's law of viscosity. The example of non-Newtonian fluid are human blood, toothpaste, and viscosity changes with velocity gradient. And if no slip condition at rigid boundaries is applicable to flow of a non-Newtonian fluid, there is a graphical representation among x-axis referred as velocity gradient and y-axis with the shear stress. There is a detailed graphical picture can be given. The ideal solid there we can conclude with various fluids are ideal fluid with shear thickening dielectric, and Newtonian fluid with shear thickening, and non-Newtonian fluid are pseudoplastic. For shear stress, rheoplastic, the ideal plastic fluid, or Bingham plastic, and for thixoplastic it is also known as ideal solid. And on non-Newtonian fluid, study of non-Newtonian fluid is called rheology. It follows Power's law and time dependent. Pseudoplastic, n less than 1 and b is equal to 0. These are shear thinning fluids. Example: blood, milk, polymer solutions, syrup, rubber solutions, gelatin, nail paint, paper pulp, etc. And dilatant fluids, shear thickening fluid. Example: quicksand condition, quicksand, saturation sugar, solution of sugar, and rice, starch, water. Bingham plastic fluids, it has some initial strength beyond which deformation starts. Example: toothpaste, sewage sludge, drilling mud, gel, cream. And time dependent classifications are thixotropic fluids, viscosity decreases with application of shear stress. Example: lipstick, ketchup, printing inks, enamel paint, jelly. And rheopectic fluids are viscosity increases with application of shear stress. Examples are gypsum paste, bentonite slurry. And buoyancy, now we are going to see about buoyancy. And buoyancy force, it is an upward force exerted by static fluid on a floating or submerged body. If the floating body is less than water density, body will sink. If the floating body buoyancy force less than water density, body will sink. If the buoyancy force greater than water density, body will lift. If the buoyancy force equal to water density, body is in rest condition. Center of buoyancy, the point in displaced fluid through which the buoyancy force is supposed to be act. And Archimedes principle, when a body is immersed in a liquid, an upward thrust equal to the weight of the liquid displaced acts on it. And metacenter, a point about which a submerged body starts to oscillate when it is tilted by a small angle. Metacentric height, Gm is equal to Bm minus Bg, which means the I minimum, which means the moment of inertia minimum divided by volume immersed minus of Bg. The time period of oscillation T is equal to 2 pi root of k square divided by Gm into G. and k is equal to least radius of gyration, and I minimum is equal to moment of inertia. Metacentric height for rolling condition will be less than pitching condition, and larger metacentric height gives greater stability to the body. Different conditions of floating body. Floating body rotation axis in different conditions are: pitching means transverse axis, and rolling means on longitudinal axis, and yawing means transverse axis perpendicular to the plane. Equilibrium condition for submerged and floating body. On stable equilibrium, B is above G and M is above G, which means buoyancy is above gravity and metacenter is above gravity. On unstable equilibrium, buoyancy is below gravity and metacenter is below gravity. For neutral, buoyancy and gravity coincide, and metacenter and gravity coincide. Metacentric heights for various ships. Merchant ship, the metacentric height less than 1 meter. For sailing ship, the metacentric height being less than 1.5 meter. For the battleship, the metacentric height being less than 2 meter, and for the river boat, the metacentric height being less than 3.5 meter. Cargo ships metacentric height will be greater than passenger ship metacentric height, so cargo ship is less comfortable. Important laws and terms. For Pascal law, pressure at a point in a fluid system is equally distributed in all directions. It is applied to fluid at rest. Pascal law is avoid if shear stress is 0. Px is equal to Py is equal to Pz. Example for Pascal law are hydraulic crane, hydraulic lift, hydraulic jack, hydraulic brake system. And for hydrostatic law, the rate of increase of pressure in vertical direction is equal to the weight density of the fluid at that point, and dP by dH is equal to W is equal to rho g, and pressure head H is equal to P by rho g or P by W. Hydrostatic force of curved surface, and Fh is equal to rho g of A x bar, and A is equal to projected area and x bar is equal to vertical distance of center of gravity of the body from the free surface. And resultant force F is equal to root of Fh square plus Fv square. Fh square means hydrostatic force at horizontal axis and horizontal force at and the vertical and the force at vertical axis. For that, resultant force are finalized as F is equal to root of Fh square power plus Fv square, and Fv is the weight of liquid block above curved surface. Total pressure and center of pressure for submerged plane. When the surface position is horizontal, total pressure will be F is equal to rho g A x power bar, and which is also finalized as specific density W into A into x power bar, and center of pressure HCP is equal to x power bar. And for vertical position, F is equal to rho g A x bar, and is also equal to W A x bar, and HCP is equal to x bar plus IG divided by A x bar. Inclined position, F is equal to rho g, the same formula for all the horizontal, vertical and inclined, but the center of pressure may be changed, x bar plus Ig divided by A x bar and sine square. For the curved surface, the total pressure may change as for horizontal rho g integration of HD A sin theta, and for the vertical force rho g integration of HD A sin A cos theta, and the resultant force for horizontal and for the vertical force are W A power A x bar. From P is equal to rho g H, the pressure does not depends upon the shape and size of the container. It only depends on height of liquid surface or pressure head. Geometric properties of some important shapes. For the rectangle, center of gravity x is equal to d by 2, and center of depth of center of pressure h bar is equal to 2 d by 3. And for triangle, x is equal to 2 h by 3, and h bar is equal to, and the h bar as center of depth of center of pressure is equal to 3 h by 4. For an inverted triangle, x is equal to h by 3 and h bar is equal to h by 2. And for circle, x is equal to d by 2 and h bar is equal to 5 d by 8. For trapezium, the center of gravity x is equal to a plus 2b divided by a plus b and of the whole multiplication of h by 3, and for the h bar is equal to a plus 3b divided by a plus 2b and for the whole multiplication of h by 2, and for half circle x is equal to 4r by 3 by or 2d by 3 by, and for h bar is equal to 3 pi r divided by 16 or 3 pi d by 32, and the unit of pressure was 1 pascal is equal to 1 newton per meter square, and 1 atmospheric 1 atm is equal to 101325 pascal, and 1 psi is equal to 6894.76 pa, and 1 tar is equal to 133.3 pa is equal to 1 mm hg, and 1 bar is equal to 10 power 5 pascal, and 1 kilogram f divided by centimeter square is equal to 9.81 into 10 power 4 newton per meter square. And also there is a comparison graph between absolute zero pressure and pressure. P absolute pressure is equal to atmospheric pressure plus gauge pressure, and vacuum pressure is equal to atmospheric pressure minus absolute zero pressure. Absolute pressure is the actual pressure at the given position. The pressure measurement devices are: for the pressure measurement we use manometer and mechanical gauges. For the manometer, there are two types of manometers, simple and differential manometers. On simple manometers, the classifications are based on piezometric only for liquid, for small and moderate positive gravitational pressure, and for U-tube manometers, positive and negative gauge pressures and high pressure can be measured, and for sensitive manometers modified from U-tube manometer, which is also classified into two, which is a vertical single column and inclined single column, and the differential manometers are classified into three as inverted U-tube, which is also known as differential manometer to measure liquid pressure, and U-tube differential manometers, and sensitive type of differential manometers, which is also classified as inclined differential manometers and micrometer differential manometers. And mechanical gauges are classified into four types: diaphragm pressure gauges, bottom tube pressure gauges, dead weight pressure gauges, and bellows pressure gauges. Methods of fluid motion analysis are: the methods of fluid motion can be analyzed by two methods, Lagrangian methods and Eulerian methods. In this method, each single fluid particle is studied for its motion characteristics, density, acceleration, etc. It is time making and most accurate method. But Euler method, in this method, the velocity, acceleration, density, etc. are described at a point or certain section in the flow field. Types of fluid flow: for a steady flow, fluid property like density, pressure, velocity does not change with time. For the unsteady flow, fluid property changes with time. For the uniform flow, at a given time, the fluid property does not change with respect to the space. Non-uniform flow, at a given time, velocity changes with respect to space. For the laminar flow, fluid particles moves along well-defined path or streamline all the streamline are straight and parallel. Adjacent layer does not cross each other. It is also known as streamline flow or viscous flow. Turbulent flow, fluid particle moves in a zigzag or in random order. Compressible flow, density of fluid changes from point to point or density is not constant in fluid flow. Incompressible flow, density remains constant. Rotational flow, during flow along streamline, fluid particles rotate about their own axis in both the circular as well as straight line motion. Irrotational, fluid particle does not rotate about its own axis in both circular as well as straight line motion. Local or temporal acceleration, it is the rate of increase of velocity with respect to the time at a given point in a flow field. Path line, it is a path travelled by the single fluid particles at the different instant of time. It represents the direction of the motion of the single fluid particle at a given time. Streamline, it is a streamline flow. Each fluid particle has definite path and the path of individual particles do not cross each other. It represents the direction of motion of any particle. And convective acceleration, it is the rate of change of velocity due to a change of position of fluid in a fluid flow. Here we see a comparison among forced vertex flow or free vertex flow. For this some external force or torque required to rotate the fluid mass. There is no external torque required to rotate fluid masses. Example: flow of water through the runner of a turbine. For that, free vertex flow through kitchen sink. Here on forced flow of liquid pass through impeller of the centrifugal pump. Liquid flow. For that, free vertex liquid flow through a hole at the bottom of the container. And for forced vertex, rotation of water in a washing machine. And for the forced vertex, the whirlpool in a river. Flow field due to tornado, and liquid flow around a circular bend in a pipe. Double dipole, double source. It is a combination of source and sink flow. Correction factor, kinematic energy correction factor. Alpha is equal to actual kinetic energy divided by kinetic energy calculated from average velocity, and momentum correction factor beta is equal to actual linear momentum per second divided by linear momentum per second calculated from average velocity. For the flow condition alpha and beta, laminar flow in pipe, the alpha is equal to 2 and beta is equal to 1.33. Laminar flow between parallel plates, alpha is equal to 1.543 and beta is equal to 1.2. And the turbulent flow in pipe, alpha is equal to 4 divided by 3 or 1.33, and for beta 1.2. Euler's equation is based on conservation of momentum principle. Bernoulli's equation is equal to P by rho g plus V square divided by 2g plus Z equal to C, which means the C is referred as constant, and Bernoulli's equation is based on the conservation of energy principle, but the Euler's equation is based on conservation of momentum principle. Each term of Bernoulli's equation represents energy per unit weight. Rate of flow or discharge, Q is equal to area into velocity. A is equal to cross section of area of pipe, and V is equal to average velocity of fluid. Unit is meter cube per second. Euler's equal as the line integral of tangential component of velocity about a closed contour in a fluid flow. Vorticity, it is a ratio of circulation and area of the closed contour. Vorticity is equal to circulation divided by area is equal to 2 omega. Equations of motions. Newton's equation of motion derived as Fx is equal to Fg plus Fp plus Fv plus Ft plus Fc. And Reynolds equation of motion, the Fx is equal to Fg plus Fp plus Fv plus Ft, and Navier-Stokes equation Fx is equal to Fg plus Fp plus Fv, and Euler's equation of motion Fx is equal to Fg plus Fp. And Bernoulli's equation as we mentioned as previous, P is equal to P divided by rho g plus V square divided by 2g plus Z equal to constant, where P by rho g is equal to pressure constant and pressure head, and V square by 2g is velocity head, and Z is equal to potential head and also known as datum head. Piezometric head is equal to P by rho g plus Z, and stagnation head P by rho g plus V square divided by 2g. And Bernoulli's equation for real fluid, P1 divided by rho g plus P1 and V1 square divided by 2g plus Z1 is equal to P2 divided by rho g plus V2 square divided by 2g plus V plus Z square Z2 plus HL. Venturimeter, orifice meter and pitot tube. For the venturimeter, average angle of convergence is 20 degree to 25 degree, and angle of divergence is 60 degree to 7 degree. It involves actual discharge and theoretical discharge. Actual discharge formula is CD into A1 A2 divided by root of A1 square plus A1 square minus A2 square root of 2GH, and coefficient of discharge of venturimeter is 0.97 to 0.99, and for orifice meter Q is equal to CD A0 A1 root of 2GH divided by root of A1 square plus A1 square minus A0 square, and A0 is equal to area of orifice, and CD is equal to 0.65 to 0.7. And loss of energy in venturimeter is less than orifice meter. For the pitot tube, theoretical velocity is equal to root of 2GH, and theoretical velocity can be given in another form as root of 2G P1 minus P2 divided by rho g. P1 by rho g is as mentioned as stagnation head, and P2 divided by rho g can be a static head.